So this is page 24 from the spirokinematics activities. So we're going to start with an origin and a vehicle that is traveling 15 meters per second that starts to slow. And then sees the light turn green and starts to speed back up. Till she reaches her original speed. And so during this initial part, the acceleration is in the opposite direction, and then the acceleration is in the same direction that they're moving. So the first event is when she slows. Event 2 speeds up. And event 3 is when she reaches original speed. So I'll set time 1 to 0, position 1 to 0 based on what what am I doing in seconds? That's meters. And velocity 1 is 15 meters per second. And then we don't know how long it takes her to slow down. We also don't know how far she travels during that period of time, but we do know that she slows to 3 meters per second. And we do know how far she travels. I apologize. That's 15 meters. But we don't know how long that takes. And then, and we don't know the acceleration during that interval of time 1 to time 2. And then in terms of time 3, we don't know the exact time, but we do know that it's t2 plus 2.4 seconds. And we don't know how far she travels. But we do know that she gets back up to 15 meters per second. So, looking through this, it looks to me like we don't know either of the accelerations explicitly. We don't know time 2 or time 3 explicitly. And we don't know how far she has traveled totally to get up to her original velocity. So, we know that V2 is equal to V1 plus A12 T2 minus T1. And we go through and look and see, are there any things we can get rid of? And yep, we can get rid of time 1. But other than that, we have two knowns that we know what V2 is and we know what V1 is, but we don't know what A12 is and we don't know what T2 is. So one equation and two unknowns is not a happy thing. And so you have a choice as to whether you want to solve this for the acceleration or for the time, because you know that you're going to have to do some kind of simultaneous solution. And so I'll just pick one. How about A12? So I'll let you do the algebra, but A12 is going to equal to V2 minus V1 over T2. And then now I'm going to look at R2 equaling R1 plus V1, T2 minus T1, plus 1/2 the acceleration times the square of the time difference. And the zeros here are there so that R2 is equal to V1 T2 plus the half the acceleration times the square of time. And so what I can do is now plug this A12 into here, which gives me and if you do additional algebra, you end up with R2 is equal to one half of V1 plus V2 times T2. So go ahead and check my algebra there. I'm looking real quick, I'm thinking. Looks good to me. And so what you want to do from there is solve this for what you don't know, and you do know what R2 is. That's the value earlier. We know what V1 and V2 are. So to get T2, I know that it'll be 2R2 over V1 plus V2. And if you want to check to see if you have made any major mistakes, what you can do is just do unit analysis. I know that time is supposed to be in seconds, and if I have position on top in meters and velocity on bottom in meters per second, that when I do that I end up with seconds, which is pretty much what I think I need to have. So I can't do the actual calculation on this screen, can I? I probably could. Why don't I just box out an area right here? And when I get to learn this a little bit better, maybe this will be more inherent. But anyways, 2 times 15 meters. And that's over if I remember correctly, it was 16 meters. Per second, and then 3 meters per second. Which would be 19, we'll call it 20. We'll call that about 1.5 seconds. And again, you can check the units if you'd like. So, let's see where to go next. From previous step, we know that the acceleration is equal to the velocity difference divided by time, and so that was 15 meters per second, not 16 like I said on the previous page, minus 3 meters per second. And that is all over. It's about 1 2/3 seconds, not 1.5, so I'll call it 1.7 seconds. And so if I have 12 divided by 1.7, 12 meters per second divided by 1.7 seconds, that would be, let's call it 7 and a little bit of change. And the units, of course, are meters per second per second. So now we have everything between event 1 and event 2. Now it's time to move on to talking about what's going on in between 2 and 3. So moving on, V3 is equal to V2 plus A23 T3 minus T2. And of all of this, we don't explicitly know A23 or T3, but we do know something about T3. And so what I'm going to do is I'm going to solve this for A23, because that's the thing I don't know. And then I'm going to remember the fact that T3 is equal to T2 plus, I think I remember, 2.4 seconds. So which would leave me right about here. And if I go ahead and plug in, I know that my final velocity, I'm back up to 15 meters per second from that intermediate 3 meters per second, and it took me 2.4 seconds to get there. And so, whipping out the calculator, it would be an acceleration for that next interval of 5 meters per second every second. So finishing up here, I think, let's consider that my final position at point 3 is equal to the initial position at point 2, or event 2, plus the velocity times the time interval plus 1/2 the acceleration squared times the time interval squared. And in all of this, the one thing we don't know is R3, and so we can go ahead and do some plugging. That R2 is, if memory serves, 15 meters. Excuse me about that. Plus 3 meters per second. And then T3, if you'll remember, is T2 plus 2.4, and when we combine that, that gives me the change is 2.4 seconds. Plus 1/2, and we figured out that the acceleration was 5 meters per second. And again, I've got T3 equaling T2 plus 2.4 seconds, so combined that gives me 2.4 seconds, and that is quantity squared. And so, with the help of a calculator, I'm thinking about 36, that's a 6.6 meters.